All right, let's go over this four square activity. Now, I'm going to work out each of the problems so that way you can check how you did. All right, so the first one says we're going to find the area inside one loop of the lemniscate, r squared equals 4 cosine of 2 theta. All right, so let me draw a picture first. I don't have the polar graphs, but that's okay. Um, we got cosine of 2 theta, right? So that means it's oriented on the x-axis, right? And your radius will be, you got r squared equals 4 squared root of 4 is 2. So you'll go out 2 units and out 2 units and doot, 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 and it's just this lemniscate. Now, encourage you to graph this. When you put it into R, in fact, here, let's do it. You want to make sure you're in polar mode, right? Polar mode right there. And when I hit y equals, you got r squared, so we need the square root. So I'll put square root of 4 cosine of 2 theta. Okay. Now technically it's plus or minus, yes, but go ahead and do it for yourself. I already did it. You will see that you end up getting the same graphs. So this isn't going to come out perfect because there are some undefined values when you plug into theta. Like for example, what's one? How about pi over 2? When you plug theta equals pi over 2, you would have cosine of pi, which will give you a negative square root, right? So on here, it's going to show up as undefined. But if you remember, it's okay for our r's to be negative in polar form. So this calculator is going to have an issue with it. So it's going to show up as kind of funky a little bit. But the only reason why I want to show you is I want to show you how this lemniscate is generated. Because when you draw it, you probably draw an infinity symbol. But that's actually not how it gets generated. When you start plugging in, you plug in a 0. It does start right here with 4. When you plug in, let's see, pi over 6, you would get a 2. So here it'll come to here. So that means it's coming this way. At pi over 4, you're going to get a 0. But then there's a whole bunch of undefined values. And then all of a sudden you get back to one where it's 0 again. And then it's going to generate this part of the curve and then come around this way. And then it'll go like that. Right? And who knew? But if you plug in values, you'll see it. Also, if you graph it, watch. Oh, okay, hold on. Let's try that again. Well, here, first of all, let me zoom in and see if I can get this to. All right, that's not perfect, but what if I move it? Maybe if I do it, I'll change it to a darker line. There we go. Okay. All right, so let's try this again. Graph. That's better. So obviously it's broken up because of those undefined values or whatever, but in reality, it's not. It's just the calculator's having an issue with it. But did you see that? Let me show you again. I hit enter and then enter again. When I hit graph, watch how it graphs. It's going to start on the positive x-axis and then trace it through like I just graphed. Womp, womp, womp. All right. The reason why that's important is you got to figure out these limits of integration. And so when I choose my limits of integration, there's a reason behind it. We want just the area inside one loop, right? So I can choose this loop. And I can't just go from 0 to this guy because, well, I could and just get half, but you're not going to be able to find the area with just one limit of just going straight up like this without going into the negative angles, if that makes sense. Like you don't start here until it's, what is it, 7 pi over 4 gets you back here and then to 2 pi. So it's a little bit weird. So two ways to do it. You either are going from negative pi over 4 to positive pi over 4, or break it up and just find the top half of the area, which is what I'm going to suggest you do, and um, then go from there and um, right. You can go from 0 to pi over 4. That works. What else works? Pi over 4 to 3 pi over 4 will also work. So here's pi over 4. You would come around. You could go to 3 pi over 4 as well. That also works. If that makes sense. Okay, so what do I want? Well, I want to figure out, when is this guy 0? We go 0 is equal to 4 cosine of 2 theta. Then that's cosine of 2 theta is 0, which is your cosine of an angle is 0 at pi over 2 and also at 3 pi over 2. But for the reason I just gave you, you can't go, right? You're not going to get the right loop. So instead, we'll go from negative pi over 2 to pi over 2. And what that will do is give you from here to here. Now, which means you're going to go from dividing both sides by 2, pi over 4 and negative pi over 4. That would give you the whole loop. You're going to also use the symmetry and go from, so here's your limits, or you also can do 2 times 0 to pi over 4. And that'll go from here, 0 to pi over 4. You're just getting that upper loop, and then times 2, since it is symmetric right there. So I say let's do this one. Yeah, we're going to do from 0 to pi over 4 and just double it. Yeah, hopefully that makes sense. And then it's of 1/2 r squared d theta. And normally we square what's in the parentheses because normally they're just giving us r, but here they gave us r squared. So you don't square it this time. It's just that guy. Yeah? All right, so then that means that I would have a, what does it become? So I've got, why am I all the way over here? I come over here. All right, so the 2 and the 2 will cancel out, so that you've got 0 to pi over 4 of 4 cosine of 2 theta, d theta. And finding the antiderivative of that would be sine of 2 theta. Chain rule would have said times 2, so I need to divide by 2. So 4 divided by 2 will leave me with a 2. Yeah. Is that right? Cosine 2 theta times 2? Yep. All right, so then that gives me a 2 times sine of 2 times pi over 4 minus 2 times sine of 0. And that's a 2 times 1. Sine of pi over 2 is just 1, and then minus 0. And so you should have gotten an area of one of those loops. That's all we wanted, was just one of the loops, is equal to 2. And the way I did it was I only found the upper half of the loop and I multiplied it by 2. And then remember, our formula for the area is we used alpha 1 and alpha and beta, I think, and then 1/2 r squared d theta. If you remember, that's how we found the area of these guys. Okay, so that's number 1. Lots of ways to do it. You also could have went from negative pi over 4. So it also would have worked from negative pi over 4 to positive pi over 4. That's perfectly fine. You will still get the same answer. If you do pi over 4, the same answer. So this time you wouldn't be multiplying by 2. It's just negative pi over 4. So that'll generate this guy. Negative pi over 4 to pi over 4 will give you that whole thing. if you do, yeah, let's just stop. There we go. For most of these problems, there is more than one way to get the job done. Just keep that in mind. You may have done it differently, but if you got area of 2, you're golden. All right, number 2 said find the area inside the inner loop of the limison r equals 2 sine of theta minus 1. All right, so that's not how you're used to seeing it. You're used to seeing it as -1 plus 2 sine of theta. You may not have recognized, like maybe you haven't seen the -1 before. If your first number in the a plus b, sine or cosine, if that guy is negative, it's the same. It's the exact same graph as r equals +1 plus 2 sine of theta. Minus sign in between changes which side of the origin that the graph is oriented on. A negative in front produces the exact same value. You want to test it out, go in Desmos, go on your graphing calculator, put a positive, graph this guy and graph that guy, identical, same exact graph. It's just how these polar graphs work out. Okay, so how does this get generated? All right, so we've got a 2 sine of theta, which means you're oriented on the y-axis. Above it, 2 plus 1 will give you 3, so you'll be going up 1, 2, 3. There's one dot. You've got 2, it's an inner loop-de-loop, so the inner loop 2 minus 1 will give you a +1 there, and then the bumps are 1 and -1. Those are your bumps. You got one at the origin. Okay, so those are the loops, and we've got a loop, right? And normally you would have just do 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 do, right? So I drew it that way. It's kind of funky looking, but whatever. But here's the deal: it doesn't get generated that way, right? You can plug in values. If you start with when theta is, you're going around this circle, right? You're starting off with theta equals 0. At 0, you would have sine of 0, which is 0. So your r would be -1. So when your angle is here at the positive x-axis, you actually start at that point right there. So when theta is 0, you're starting there. And then we got to see, where does it go after that? I'm going to just plug in friendly numbers. When is it friendly? Well, on the short triangles, right? So when sine is pi over, so when theta is 0, r was -1. So that's how I knew it started there. You could plug in all the numbers. I'm going to just plug in friendly ones. If the friendly ones don't help you figure out which way it goes, then you can plug in more. If theta is pi over 6, that's the 30-degree reference angle, right? And so that's a short triangle. So sine of that would be 1/2. So you have a -1 plus 1. Your r is 0. Oh, so that means it comes to here. Yeah. And if you do pi over 4 and pi over 3 are going to be decimal answers. What if I jump to pi over 2? All right, well, now I've got -1 plus 2, so your r is 1. So it goes like this. So this graph is actually generated starting right here, going around, and doing the loop-de-loop that way, and going all the way around. And let's confirm it on here. Okay, so I want a -1 plus, I'll zoom in, -1 plus 2 sine of theta. Okay, and watch how it gets generated, right? Graph it. Yeah, theirs looks much better. But did you see how it started here and then went around that way? Okay, so why do I care about that? Because it kind of gives me a hint on what these limits are. All they want is the area inside the inner loop. So all I need to know is it's being generated this way. I need to know what angle is this 0? And then when does it hit 0 again, right? Because it got generated that way. All right, well, I got one of them right there. But here's how you can solve it. You're going to set r equal to 0. Add the 1, divide by 2. So when is sine of theta equal to 1/2? Well, when theta is pi over 6, and again at 5 pi over 6. The two values when this guy is 0. So that's going to generate the area inside that loop there. All right, so your area is from pi over 6 to 5 pi over 6 of 1/2 r squared d theta. And this time your r is -1 plus 2 sine of theta. Yeah. Oh, I forgot to square it. Square it. Don't forget to square. Okay. I'm just going to pull this 1/2 out front. I got a 1/2 from pi over 6 to 5 pi over 6. Squaring this guy will give me a 1. And then 2 times -1 times 2, so that's a -4 sine of theta, and then plus 2 sine squared would be a 4 sine squared of theta, d theta. And then I told you about this trick of sine squared, not easy to integrate. In fact, you can't because of chain rule. So you're going to rewrite it. And I've taught trig for so long that I have my double angles I memorized. So I know cosine of 2 theta is 1 minus 2 sine squared. Solving for sine squared, I'd add that over, subtract the cosine, and divide by 2. Okay, so here's the identity you got to memorize, is that sine squared is equal to 1 minus cosine of 2 theta over 2. And that's easy to integrate. So this is a 1/2 pi over 6 to 5 pi over 6 of 1 minus 4 sine of theta. Both of those will be easy to integrate. This guy becomes a plus 4 times the quantity, 1 minus cosine of 2 theta over 2. Yeah. So then this, go ahead and simplify this. This 2 goes into the 4 2 times. And then I need to distribute that 2 to the 1 and to this negative cosine. So I've got a 1/2 out front, still pi over 6 to 5 pi over 6. This will end up giving me a 1 plus a 2 times 1. So my constant ends up being a 3. Minus 4 sine of theta, and then a 2 times negative cosine of 2 theta. Like that. All right, we can integrate now. I still have this 1/2 in front. Antiderivative of 3 would be 3 theta. Antiderivative of 4 sine of theta would be a 4 cosine of theta, but that's a negative, so a positive 4 cosine of theta. Antiderivative of cosine of 2 theta would be a sine of 2 theta. Chain rule would have said times a 2, so it's just a -2 sine of 2 theta. Yeah. And then we're going from pi over 6 to 5 pi over 6. All right, so I've got a 1/2 times, plugging in the 5 pi over 6 first. So 3 times 5 pi over 6 plus 4 times cosine of 5 pi over 6 minus sine of 2 times 5 pi over 6. All right, so that was 5 pi over 6. Subtract from it. Super important you put parentheses around the second guy. 3 times pi over 6 plus 4 times cosine of pi over 6 and minus sine of 2 times pi over 6. All right. What does that become? 5 pi over 2 plus 4 times cosine of 5 pi over 6 is a negative rad 3 over 2 minus sine of 5 pi over 3, that's quadrant 4, that's a negative rad 3 over 2. Right, and then a minus, and then I'm going to go ahead and keep these parentheses for a minute. That would be a pi over 2 now, plus 4 times cosine of pi over 6 is rad 3 over 2, minus sine of pi over 3 is a rad 3 over 2. I don't know, I might have too many there, but whatever. Okay, so what does this become? Got a 1/2 in front of everything. 5 pi over 2. What's that? Some of the over 2 stay and some of them cancel. So let's do this. I'm going to keep the over 2s. I'm not going to, even though I know 2 goes into 4, I'm going to have to simplify it anyway. So I'm going to leave it. So this becomes a negative 4 rad 3 over 2 plus 1 rad 3 over 2. Distribute this minus sign into all of those guys. So you got a minus pi over 2, a minus 4 rad 3 over 2, and a minus a negative, so a plus rad 3 over 2. And then combine like terms. I still have this 1/2 out front. 5 pi over 2 minus pi over 2 would give you 4 pi over 2, which is 2 pi. And then negative 4 plus 1 minus 4 plus 1. What is that? A negative 6 rad 3 over 2. Now, distributing the 1/2 would give you a pi minus, all right, the 2 goes into there, but then we also have the 2, so it ends up being a 3 rad 3 over 2. Yeah. All right. One way, if you don't get this exact answer, the approximation is 0.544. And so just put whatever your exact answer is in and compare, right? Because you could have done it a different way. Did you remember if you only, there's symmetry involved. You could have found just half of that little inner loop and then times it times 2. Lots of different ways of doing these. So if you get a slightly different exact answer, you can always double check it by the decimal approximation. You also have your graphing calculators too, so you can check the decimal approximation that way as well. Okay, so that was number 2. Number 3 was more complicated. Find the area shared by the circle and the cardioid. Oof, okay. Well, first of all, you're not used to seeing the cardioid that way, so let's change it. That's 2 minus 2 cosine of theta. All right, so what does this graph look like? Let's start with this guy. Cosine oriented on the x. The bigger part is to the left of the origin, 4 units out. So let's go 1, 2, 3, 4. Got a point here. 2 are the bumps, so up 2 and down 2. Yeah. So this cardioid looks like that. It's a little funky, but yeah. Okay, there's the cardioid. The circle r equals 2 means you're centered at the origin and your radius is 2. So 2, 2, 2, 2. A little funky looking, but whatever. Okay, so we're finding the area shared by the circle and the cardioid. So what is the shared part? We want the area inside there. Inside these little bumps and inside this circle. We want that area there. More than one way to do this problem. Lots of ways of doing this problem. I'm going to tell you what way I think is the easiest. I think that the easiest way is to do the area of these, I'll call them butt cheeks. The area of these two little bumpy bumps. Yeah. Find the area of that and add it to the area of, what the heck is that? That's just a half of a circle. We're going to do the area of the cheeks plus the area of the half circle. All right, well, this one you don't even need calculus for. If you do calculus on it, it'll work. It'll give you the exact same area, but we know that area of a half circle is 1/2 pi r squared. Easy peasy. 1/2 pi times your r was 2. So this guy is, what, 2 pi. Yeah, so don't forget to add this when we get done, because I'm going to do a bunch of calculus on this part, right? But don't forget to add that 2 pi back in there. Okay, so I need the butt cheeks. Yeah, and I can also use symmetry, right? These guys are totally symmetric to the top cheek is totally symmetric to the bottom cheek. Let's figure out, where does this start? When cosine is 0, you start at 0. All right, and then as you go around, let's see, cosine of pi over 3. At pi over 3, you would have a 1/2. So at pi over 3, you're at 1. How about pi over 2? You're at 0. So just integrating from 0 to pi over 2, the area of these cheeks, I'm going to integrate from 0 to pi over 2. That'll generate this area here. And then I'm going to multiply that times 2 to get me the bottom cheek also. Yeah. It also works if you went from, this guy would be negative pi over 2 to positive pi over 2. That'll get you that guy. Anyway, so more than one way to do it. I think this is the easiest way. And then it's 1/2 r squared d theta. And your r this time, you're just on the cardioid. So it's the 2 minus 2 cosine of theta. All right. Yeah, okay. I can take this 2 and this 1/2 and they cancel, right? So now I've got from 0 to pi over 2 of, expand this out, 4 minus 8 cosine of theta plus 4 cosine squared. And if you remember, cosine squared is the cosine 1 plus cosine of 2 theta over 2. That's the identity of the double angle identity. So I'm going to replace that. All right, so now 2 goes into 4 2 times. And so then I'm left with 0 to pi over 2 of, when I distribute this 2 into the 1, and don't forget, it's into both. Yeah, you would have a 4 and then a plus 2. So that leaves you with a 6, and then minus 8 cosine of theta, and then plus 2 cosine of 2 theta. So now I'm going to find the antiderivative now. 6 theta minus 8 sine of theta. Derivative of cosine is sine, so it would be a sine of 2 theta. Chain rule would say times 2. I've got it there, so it's just a plus sine of 2 theta, and from 0 to pi over 2. All right, we'll just plug it in. First guy would be 6 times pi over 2 minus 8 times sine of pi over 2 plus sine of 2 times pi over 2 minus 0 minus 8 times sine of 0 plus sine of 0. All right, those all zero out. Nice. This is what? 3 pi minus 8 times 1, and then sine of pi is 0. So this ends up being 3 pi minus 8. Not my final answer. This was only the area of just the cheeks. But we wanted both the cheeks and this half circle. So don't forget this guy, bring it down here. So add 2 pi for the area of the half circle. And so your final answer should have been 5 pi minus 8. In decimals, that is 7.708. So just in case if you get a slightly different answer, you're not sure if yours is correct, put it in your calculator. If you get the same decimal approximation, you're golden. You're totally fine, because it's quite possible that your answer looks a little bit different from mine. Okay, last one was the most complicated one, right? Let me point out the difference between why I didn't have to do, look back at this picture real quick. I didn't have to do R2 minus R1. Yeah, I didn't have to do R2 squared minus R1 squared, because all I was doing was finding the area inside the little bumps of the cardioid. Had they asked you, let's even just only look at the right-hand side of the graph. Had they asked you for the area, let's say outside of the cardioid, but inside the circle. Oh, I don't even know. There we go. Outside of the cardioid, but inside the circle. That would have been, I'll do a different color, about green. If it had said outside the cardioid, inside the circle, it would have been all of this area. Yeah. And as you draw sectors, remember, we're not separating these into rectangles anymore. We're separating them into wedges or sectors of a circle. And as you draw out these sectors, okay, now you're hitting both the, let's go with just this sector here. Obviously, we wouldn't take that big of a one, but you're hitting the outside, you're hitting the circle, and on the inside, you're hitting the bump of the cardioid. This sector. Outside is the circle, inside is the cardioid. And so here you would have had to do your R2 would be the outside circle, your inside would be the cardioid. Yeah, and then of course you would limit your limits. But I just want to point out, like, why didn't we have to do R2 squared minus R1 squared? Because you were only finding the area on the inside of the bumps of the cardioid. It wasn't both of them. Like, you didn't have to subtract this value. Okay, different from number 4. Number 4, we're going to be subtracting. Is this one. We want the area inside the 4 petaled rose and outside the circle. All right, so what does this look like? It's a cosine, so I've got a peak or a petal on positive x-axis going out 4 units. And going up, and then they would be 2 pi divided by their 4 petals. So 2 pi divided by 4 gives you pi over 2 apart. So they'll be there, and 1, 2, 3, 4 there, and 1, 2, 3, 4 there. And so my petals, I can do them nicely, look like not too shabby. Looks something like that. Yes. So we want inside that, but outside the circle, r equals 2. So r equals 2, r equals 2, r equals 2. So here's the circle. All right. So we want inside 4 petals, but outside the circle. So I want the area of these guys. There's 4 of them. That one, that one. I want all that green shaded area. Yeah. All right. So let's see how this guy is generated, right? R equals 2 would just start here and go around to 2 pi. That's easy. The 4-petal rose does not. The 4-petal rose, if you plug in a 0 here, you would have cosine of 2 times 0. Okay, so 4. So you really do start your first point when going around the circle, you would start here. When theta is 0, your R is 4. And then, which way does it generate? Yeah. So, how about pi over 2? At pi over 2, you would have cosine of pi, which gives you -1. So when your theta is pi over 2, you're actually down here. So maybe I need to plug in some more. Let's go with, when is it friendly? Cosine of pi over 6. Okay, so let's do, okay, so when theta equals 0, your R will equal 4. How about when theta equals pi over 6? It would be cosine of pi over 3, which is 1/2 times 4, so your R is 2. All right, so you're going around. That would be like there, right? Pi over 4 is going to give me a decimal. Pi over 3, oh, that'll work. All right, so when you got pi over 3, you'd have cosine of 2 pi over 3, which is a -1/2 times 4, so your R is -1/2. -2, sorry. Okay, so you got pi over 3 would be this line, but you're actually going to a -2. That point right there is when it's, yeah, does that make sense? So you're starting here, you go to there, you go to here next. Oof, which means that this guy actually gets generated this way. Starts here, goes down, comes around, comes up. It's going to go this way, comes up. It's going to go that way, comes back, and then it finishes off the bottom of that loop. Yeah. Okay. So, couple different ways of doing it. Should I show you what the graph on here looks like? Yeah, probably. Okay, so let's do that. I'm just going to graph just the loop, or just the petal graph. Okay, so 4 cosine of 2 theta. And you can see how it, which direction it's generated. Watch the graph on how it starts. We're going to start at the positive x-axis, and you're going to see it go loop-de-loop and go down to the negative y-axis first when it does that loop. Here we go. Womp, 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 womp. Yep, there you go. Why does that matter? Because this part right here is actually 2 pi to bring you back up here. So wherever that's 0, when your R is 0, what would it be? Pi, 7 pi over 4 to 2 pi, I think, is what will give you this last little loop-de-loop. So you can't just go from 0 to 2 pi or whatever. Like, you got to change up your limits, if that makes sense. All right, so how am I going to handle this? Well, first of all, I'm not going to do every single one of these. I'm going to say, okay, there are 4 of these petals, right? So my area will be 4 times whatever I still got to come up with my limits, right? And it's a 1/2. Okay, which one's outside, which one's inside? As you draw a line going through, do you see that outside, inside, right? So what goes on the outside is your R2. So this is a 4 cosine of 2 theta quantity squared minus the inside was R equals 2. So just 2 squared. Yeah. All right, how do I get my limits? Well, what you really want is where these guys are intersecting. Now, more than one way. I'm just going to show you. If I want to just find the area of this one loop right here, how would I do it? Especially since now that I know that it actually generates this way. How do I do it? You just use a negative angle instead of a positive one. Because if you use a negative angle, then it'll start here and then come around this way. All right, so I want to know their intersection points. So when these r's are equal, right? So 2 is equal to 4 cosine of 2 theta is what I'm solving for. Dividing both sides by 4. Cosine is 1/2 with a pi over 3 angle. And the other time is when it's 5 pi over 3 is when it's positive, right? But I'm not going to use 5 pi over 3 because that would have been meow, 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 right? Okay. Instead, I'm going to use negative pi over 3 cosine. Now that's equal to 2 theta. My angle is 2 theta, so then I need to divide both sides by 2 and get a pi over 6 and a negative pi over 6 is what my theta values will be. Negative pi over 6 obviously is smaller, so that's going to give you your lower limit, and then positive pi over 6. And if you plug these values in, you'll see negative pi over 6 is what's going to generate. You should get a value of 2, and then it'll generate this curve, this part of the curve, just from there to there. All right, and now it's just some cleanup. Actually, I'm going to pull this 1/2 out and change this 4 into a 2. Make my life easier. Yeah, so that's a 2 times the integral from negative pi over 6 to positive pi over 6 of 4 cosine of 2 theta squared is 16 cosine squared, still of 2 theta. Don't square the 2 theta also. It's like if you're taking cosine of 45 degrees and you square it, you don't square the cosine and the theta, you just square. It's really what you're doing is you're finding cosine of 45 degrees first, the red 2 over 2, and then you're squaring it. So you don't square the angle, just the cosine. Now, okay, and then minus 4, okay, theta. You're going to rewrite this. All right, so from the last one, we know cosine squared is equal to 1 plus cosine of 2 theta over 2. Yeah. But that means I've got cosine squared of a different angle right now. Right now, my angle is 2 theta. So that's a 2 theta. So it's 2 times 2 theta, if that makes sense. So when I rewrite this guy, I've got a 16 times the cosine squared of 2 theta is a 1 plus cosine of 2 times 2 theta, so 4 theta over 2, and then minus 4. All right, I can go 2 goes into 16 8 times, so that I've got 8 times 1 and an 8 times this. 8 times 1, but then minus 4 will leave me with a 4 plus 8 cosine of 4 theta. And then I've got 2 times 4 theta plus antiderivative of cosine would be sine. It would be sine of 4 theta. Chain rule would have said times 4. So I need to divide by 4. 8 divided by 4 will give me 2. All right, I'm ready to plug it in. I got a 2 out front. 4 times pi over 6 would be, what, 2 pi over 3 plus 2 times sine of 2 pi over 3. That's a rad 3 over 2. And then minus 4 times negative pi over 6. That's negative pi over 2 pi over 3. Plus a 2 times sine of negative 4 pi over 6. sine of negative 2 pi over 3 there. So it's a negative rad 3 over 2. Okay. I'll leave this 2 out front. This becomes a 2 pi over 3 plus a rad 3. Distribute this minus sign into both of those guys, and you end up with another plus 2 pi over 3 and a plus rad 3. Okay, so that's a 2 times 4 pi over 3 plus 2 rad 3. Distributing the 2, 8 pi over 3 plus 4 rad 3. If you have a slightly different answer, but the decimal approximation is 15.306, and you did it right. Yay! All right, here we go. I hope you all are having a fabulous day, and I will see you later.